In this tutorial, we will learn how to include the effects of solar radiation in VOLTRA using the solar processor. This tutorial focuses on opaque materials. In the next tutorial, we will explain how to define glazing systems. In the previous session, we learned how to download an EPW weather file and link it in the functions window. We will now extend that process by linking solar radiation data from the same EPW file. Open the functions window and create a new function with the reference G01. This function represents global radiation on a horizontal plane. Link it to the EPW file for Brussels City. Next, create another function with the reference D01 for diffuse radiation on a horizontal plane, and link this as well to the same EPW file. Now click on the solar data icon in the top toolbar. The latitude and longitude of the location are automatically read from the solar radiation functions G01 and D01, which are connected to the EPW file. The next step is to define the orientation of the model. You need to specify the orientation angle, inclination, and tilt of the surface. The black line in the preview indicates the north direction. And if the orientation angle is set to 0, x-axis is the north direction, so this facade is south-oriented. If the orientation angle is set to -90 degrees, the wall is oriented towards the west. To better understand the orientation, close this window and activate Show BC. When you reopen the solar data window, you will see that the interior side lies on the east. You can also modify the inclination and tilt. If you set the orientation to 0 degrees and the tilt to 90 degrees, the wall behaves like a roof. If you choose a fixed sun position instead of the real sun path, you must manually define the solar radiation, either as a constant value or by using a function, and also specify the incoming radiation direction. For this exercise, we simulate the west facade using the real sun path. Although we have defined the solar parameters in the solar data window, they are not yet active. To activate solar radiation, open the colors window, select the external boundary condition with color 170, and toggle the sun option to yes. This enables the solar load. Next, we must define the solar properties of the materials exposed to the sun. These properties determine how much the material heats up under solar radiation. For each material, define the solar reflection and solar transmission. In this example, we add a new coating layer with a thickness of 1 cm and assign it color 57. Name this layer, coating. Since the coating is opaque, set the transmission to 0. By default, the reflection is 0.1, which means 90% of the solar radiation is absorbed. This represents a dark-colored surface. We first run a baseline analysis with this dark coating. Go to the Edit menu and select Report Definitions. For color 57, corresponding to the coating layer, define the maximum temperature as the output parameter. To better visualize the solar impact, go to Calculation Parameters and change the calculation start time to day 160 at 9 o'clock hours. Then click Calculate to run the simulation. Once the calculation is complete, open Text Output and go to the Report Output tab. Copy the results and paste them into a spreadsheet. These values will serve as the baseline for comparison. Now modify the surface reflection of the coating layer to 0.5, which corresponds to 50% reflection and 50% absorption. This represents a light-colored surface. Solar reflection values for different colors can typically be found in product manufacturer datasheets specific to your project. Run the calculation again. After completion, open the text output and copy the new report data into the spreadsheet. Create a graph comparing the maximum temperatures of the coating layer for 90% absorption and 50% absorption. In this example, we used a global exterior surface coefficient of 25 watts per square meter Kelvin, which corresponds to high wind speeds. If a lower coefficient, such as 13 watts per square meter Kelvin, were used to represent lower wind speeds, even higher surface temperatures would be expected. In the next step, we explore how to include solar obstacles in the model. We distinguish between obstacles that are far from the model, such as neighboring buildings or trees, and obstacles that are close to the model, such as shading devices. Distant obstacles are defined using the sun obstacle option, while nearby obstacles are directly modeled within the geometry. To define a distant obstacle, click on the sun obstacles icon in the top toolbar. A sun obstacle is a spherical rectangle defined by azimuth and altitude coordinates within direct solar radiation is blocked. This can be viewed in the graphical output. Enable sun position and then sun obstacles. A gray zone appears, indicating the default 5-degree shadow. Each sun obstacle is defined by 4 parameters: minimum azimuth, minimum altitude, and maximum altitude. Insert a new row by clicking Insert After. As an example, define a nearby building with an azimuth range from 45 to 90 degrees and a maximum altitude of 60 degrees. Enter these values in the sun obstacles window. Return to the graphic output to preview the obstacle. When the sun is gray, it is behind the building and only diffuse radiation reaches the model surface. When the sun appears yellow, also direct radiation reaches the surface. For obstacles located close to the facade, such as shading elements, it is better to model them directly in VOLTRA. First, adjust the settings of the second obstacle as shown. This obstacle is created to block the sunlight coming from the interior side, which could lead to an incorrect simulation result. Switch to the minimum grid view to simplify modifications. Add 2 new grids in front of the coating layer. Set grid 2 to 20 cm and grid 3 to 5 cm. Then split the Z direction cell twice. Select the Z cell, go to grid and choose split, or press Ctrl+I. Select border 2 and enter 30 cm. Then select the 30 cm cell and repeat the process, this time entering 25 cm. Next, go to blocks and create a new block. Assign color number 8 for aluminium. Define the block from X1 to 2 and Z1 to 2. Check boundary condition and enable auto split grid for calculation. Then click Calculate to run the analysis. After the calculation is complete, open the graphic output. Enable sun position and display the absorbed solar heat fluxes to observe the shading effect on the facade. Adjust the range for better visualization. You can now review the results for each time step to clearly see how the shading element reduces solar gains. Once finished, close the graphic output window. Thank you for watching, see you in the next tutorial.